equipped.
So next we have Imam, and he's going to talk about implicit multicore parallelism using CnC-Python.
Sorry? The mic?
You can use either one.
Oh. Okay. Hi, everyone. I'm going to talk about CnC-Python, and I guess we've already had a taste of all these multi-cores and GPUs and why parallelism is important, so I'm not going to delve into that much. So some acknowledgements. These are people in my group, and the project was co-funded by Intel and also an NSF project, and also the people at Intel who developed the concurrent collections model, which I'll explain shortly. So at Rice, the project I work on, we are focusing on these top two pieces. We believe that there is a large group of people who don't necessarily write or know how to write parallel programs. And that's why we have this problem, and we're trying to solve that, how to make writing parallel programs easier. So this talk is going to focus on writing parallel programs without actually writing parallel code or using parallel constructs. And it's built on top of a framework we built for the lower piece, which is a language where you can write explicitly parallel constructs. That is not in Python, but I'll show you how we can use that to execute Python code. OK, so the issue is writing parallel programs is hard, and I guess anyone who's tried that already knows it. And those who haven't, don't try to write parallel programs explicitly. OK, and then it's even harder in Python because the standard CPython it doesn't support multi-threading, which is almost the de facto everybody tries to do when they write parallel programs. And it does support multiprocessing, but multiprocessing, you have to handle data communication, and then there are blocking constructs where if you're trying to read data and it's not available, your thread blocks or your process blocks, and it's just wasting CPU resources. So then the solution to this is, at least one solution proposed is this concurrent collections model proposed by Intel. So what they claim is, if you want to write a parallel program, don't specify what operations will execute in parallel. Just specify the semantic constraints, and then the runtime will handle extracting parallelism from your application. And then what are these semantic constraints? There are only two such semantic constraints: a producer-consumer relationship and a controller-controllee relationship. Where, so a producer-consumer is, I guess, easy to understand. A controller-controllee is you only launch some task if some other task is executed. Yeah. OK. And what are these semantic constraints? Normally, they're data dependencies and control dependencies in your application. So you specify these constraints in some form of a graph. You basically write a text file that defines your graph. And then you write some computational units, which are basically just serial code. They could be in any language of choice. In CnC-Python, it's Python. And then the runtime takes care of handling the dependencies and executing your code in parallel. If there is no parallelism to exploit from your application, then the runtime won't be able to. But if there is, then the runtime will parallelize your application. As you, as a programmer, don't have to worry about writing parallel code. OK, so what are the code constructs in CnC? So the oval is used to represent computational units. They are called steps in CnC. You usually have simple brackets around them. Step needs some data to operate on. So the boxes you see are input data, and then it's going to output data. Steps are supposed to be functional, so they don't mutate the data they receive. And in CnC-Python, we can enforce that. And you output data, and then hopefully some other step picks up the data which you output. And you need tag collection or control collection, according to CnC, to spawn this step. Or in CnC terminology, it's called prescribing a step. So these are all the constructs you need to define a CnC graph. Once you define a CnC graph, you can let the runtime get loose. OK, so then the two semantic constraints are producer-consumer. That's on the left. And controller controllee, that's on the right. So the controller controllee is when a step executes, it notifies the control collection that, oh, I'm done executing. You can spawn off more tasks. So these are just the two constraints you need. OK. And what you get if you use CNC, so CNC is a coordination language. Your actual computational steps can be in any language you choose. The runtime handles spawning the task, so you don't have to bother about it. It's single assignment and deterministic, because if you don't allow mutations and steps are supposed to be functional, you can guarantee that it's deterministic. And because you don't mutate your data, you don't have any data races. OK, so try a simple example on how to write a CNC program. This is just a toy example, so don't expect any performance if you write this example as your CNC app. OK. So the example I'm going to try out is Cholesky. It's a triangular factorization problem. You use it to solve linear equations. If you can factorize your matrix, you can then solve linear equations easily. And this is basically the formula to compute the lower triangular matrix. And in Cholesky, if the matrix satisfies some constraints, then the upper triangular matrix is just a transpose of the lower triangular matrix. So if you were to write this in Python, we'd probably write something like this. A bunch of nested for loops, and then an aggregation of the result at the end. It's working on NumPy arrays here, and yeah, just basically reading and writing data. And this one has been written to be functional, so there is no mutation of data anywhere. You could do away with one of the matrices or one of the indices if you were to write it in a non-functional form. But this is just an example of how you would write it if you were writing a functional version of Cholesky. So how do I transform this into a CNC application? So first, you determine all your computation points. So the comments in blue on the right indicate all the different places where computation is happening. And the for loops are in a manner determining when the next computation can proceed. So those are like your control dependencies in your application. And of course, there are data dependencies, because you're modifying an item somewhere, and in the next iteration of the loop, that data is being used to compute the next element, and so on. OK. So given this structure of the program, how do you define a CNC version of it? So we had those 3 for loops. So you can see those 3 as the 3 control collections on the top. They are going to spawn the different instances of the steps. Each of the steps in the for loops, you can define them as steps. And there are 3 of them. And then there is one at the end to aggregate the result. And then you define your item collections or sources of data. And then you just draw arrows and, OK, this step is going to consume data from here, and is going to write data to some other place. So the arrows are directional, representing input and output. OK. And then there is something known as the environment, which basically you need to feed in data to your graph to start off the computation. So the environment is responsible for feeding in data to your graph. And then once the whole graph finishes computation, the environment is going to read out the results. So in this example, the environment is going to populate the initial matrix, and then it's going to read out the results. OK. So now this is what you'd have to write as a CNC programmer. If you have this diagrammatic representation of your CNC graph, you'd have to define it in text form. It's simple translation of that graph into text, where you say, oh, these are my item collections with square brackets. And you type them. You say, we were using indices. So in our implementation, we represent indices with the data type called point. So you're saying that a point goes to a double. The point could be a 3-dimensional point. So it's basically mapping a 3-dimensional point into a value. And then the result is the aggregated value, which is the 2-dimensional array. And then you have the control collections, which determine who spawns off the steps. So each of these control collections spawn off the 3 different types of steps. And then you have to actually define what are my inputs and what are my outputs. So in this example, step 1 is going to read from A2, and write to T and also to the control collection C2 because it needs to tell C2 to spawn off instances of step 2. And then you define what the environment is going to read and write. Okay, so once you've defined this CNC graph, what do you have to do? We provide a tool called CNC Translate. You need to run your CNC file against this tool, and it's going to generate a whole bunch of code. It'll generate some Java and then some Babel-specific APIs. I'll get to that a little later when I discuss the implementation. And it's also going to generate stubs for your Python code. That's where the user can fill in his actual own Python. And there is no restriction to the Python you can write in there. It's any Python goes. And then once you have your Python code ready, you do a build, which it links to these Python code you've written and generates a compiled version. And then you can launch it with however many number of worker threads you want. And then get your output. So the user only writes a CNC specification and then some Python code to solve this problem. And then the runtime's going to extract any parallelism there is. So what kind of Python code can you expect to write? So I'll get to the create awaits list later. Let's look at the compute. So the compute is basically the larger font line where V3 is V1 by V2. That's the actual computation you're doing. Everything else is just runtime overhead. But that's computing T of JK, KK plus 1, A2 by T. So that's all it's doing. So before you can do the computation, you need to retrieve your data. So retrieve values from A2 and T, and then write to T again. The create awaits list is a feature required by our runtime. Our runtime doesn't want to spawn a task if it knows that data is not ready for the task. Because if you spawn such a task, it's just going to block and wait for data to arrive. So you're just going to waste your CPU resources. So the create awaits list just lets the programmer define what are my data dependencies and only launch me if these dependencies are satisfied. This could be generated by the compiler or by our translator, but it requires some additional information in the CNC graph. The one I presented was a very simple one, so it didn't auto-generate these dependencies. The programmer had to write this down by himself. Okay, so that's basically just a simple snippet of what Python code you'd have to write, and then that's it, you're done. Okay, so how is the runtime actually implemented? So I already mentioned this issue with multi-threading and multiprocessing in the Python interpreter. And then also we're going to be launching many tasks, and we need a work stealing runtime and some mechanism to run the task in a lightweight manner. And we felt Python was not the best place to write such code, and it's not the best environment. So what we have is a language called Habanero Java at Rice. It's a language that runs on the JVM, and you can write perfectly fine multi-threaded code on the JVM, and it runs fine. So we have our core CNC runtime implemented in Java. And the only time we ever want to interact with Python is when we actually want to do the computation. And so anytime the runtime decides, OK, I need to launch a computation, it hands over the input data or the control signals and asks the Python interpreter to run that Python code for it. And since we're coming from Java to Python, and sometimes we even need to go back from Python to Java, we need an interoperability layer in between. So for that, we use Babel, which is a tool developed at Lawrence Livermore. So I think I've already spoken everything I need to for these two. So one key thing to mention is all data you allocate that stays in your Python runtime. It never percolates back into the Java runtime. Only signals and like some step has completed execution or what are the dependencies, that is the only information that goes between the Java and Python layers. So those are basically just strings, and they are very low overhead. There is no actual data copying. If you're allocating an array, that stays in your Python runtime. That doesn't go back into the Java runtime. And also, since we're using Babel, Babel actually not only supports Python, it supports C, Fortran, C++, Chapel, so on. So you can imagine writing your CNC computation where one step is in Python and another step is in C, and another step is in Fortran, and it would all work seamlessly. You can also imagine writing everything in Python at first, and then slowly transforming one step at a time into another language. That's actually our use case for the CDSE project. We have domain experts who write their code in Python and MATLAB, and they're not concerned about performance yet. They just want to get it working. And once they have it working, they hire developers to say, oh, I've written this, now speed it up for me. And then they convert it to C or Fortran. Yeah. OK, so how does the actual computation happen at Python? If we only had one Python interpreter running the computational steps, then we would run into the same problems where, because of the global interpreter lock, you can't have multiple computational steps running at the same time. So what we have is, per worker thread, we launch a separate instance of a Python interpreter. And so every time the Java runtime asks the Python, the main Python interpreter to do some work, it just hands off that work to a child interpreter that's running in a separate process. And since it's running in a separate process, I can feed it in input data, and because I already know its data dependencies, and just read back the output data. And while executing the step, if that step decides to mutate its input data, that mutation never comes back. Only the outputs it publishes is what comes back to us. So we can ensure that you're not mutating any input data, and so you don't have race conditions. So here's actually what happens. Habanero Java runtime says, oh, execute some step. It prepares all the data dependencies, sends it to the child process, lets it run and finish running, give me the output, and then gets the output, puts it into the data collection, and hands off control back to the Java runtime saying, OK, I'm done executing one task. What do you want me to do next? OK, so getting into results. We actually, so it was multi-core, not many cores. So I don't have thousands of cores to present, but 8 is good enough, I guess. We use CnC-Python, and the only other framework I found for Python was Parallelism, which tries to hide away the multiprocessing module from you. I'm not aware of other high-level Python frameworks, but I'd be happy to know if I missed out any. And then the other Java and Babel versions. So here's a benchmark used by Parallelism. So it basically sums up all the primes in some given range. And so here are the numbers if you use Python, Parallelism, and if you use CnC-Python. What we're saving here is Parallelism uses blocking constructs. Every time you want to read a data, you do a get, and you block until the data becomes available. But in CnC-Python, since you're explicitly defining your data dependencies, the runtime is smart enough not to try to read data if it's not available. It only launches tasks when it knows that all gets will succeed. So you're saving on you're doing non-blocking computations. And also the actual runtime is truly multi-threaded because it's running on the JVM, as opposed to Parallelism where everything runs in a main Python process, and anytime you're trying to do multi-threaded computations, you're running into the serialization issues. And then here's actually what happens with Cholesky. This is not the version I presented. This version does some bit of tiling because otherwise, if you're only doing one step of computation, the overhead will dominate. So here's the results. If you use different tile sizes, all of them show similar results, and there's a nice scale down. There's a super linear speed up between 2 and 4 workers. It's because of how the runtime is implemented. So you should read 2 more as 1 and 4 more as 3, because one thread is busy doing the runtime work, so that's actually not participating in doing the computation. So if it's 1, 3, 5, and 7, you can imagine that it's almost perfect speed up. OK, so summarizing, if you use CnC, you don't have to write any explicit parallel code. You just write serial code, and there's no restriction on the Python you write in your serial code. And once you have your CnC graph defined, you can expect the runtime to extract the parallelism for you. And the other benefit is CnC ensures that your result is always deterministic. So if you have a bug in your program, no matter how many worker threads you use, you'll always see that bug. If you get some result, no matter how many worker threads you use, you'll always get the same result. So an initial release of CnC-Python is already available. Feel free to download and email for feedback. Yeah, I'm happy to take questions now.
A few minutes for questions if anybody has any.
Yes.
Is there any shared memory?
So this only works on shared memory machines. It's developed for multicores. Okay. Yes.
Have you thought anything about doing? So I've seen a couple of talks on things like the sort of task dispatching approach to parallelism, and it's sort of good news and bad news. The good news is it seems like it scales very well, but it also starts to look like queuing systems, and my experience with queuing systems has not been great. But
So
having said that, you have an opportunity to maybe look at resource issues too, right? If I have a particular task that is in principle ready to go, but it needs so much memory that it can't run in concert with a couple of others, then you could defer that task until it will perform properly.
Yeah.
And kind of get at this other dimension of performance where you start to run into like memory, kind of memory.
So I haven't looked into resource bottlenecks yet,
Okay.
but you can imagine tasking frameworks handling that resource allocation issues too. That's not, I have not come across a tasking framework that does
It's on
that.
your radar.
Yeah.
Okay, great.
No questions? Okay, if not, let's thank our speaker again.
Okay.